Get started, who cares? Okay, Orchid, you're up.
Alright. Okay.
Holy wait. Why is this like... Is it like 2 centimeters long? Put it on the other side of the mic.
This is live, by the way.
That's alright.
Did we turn it off? Oh, we broke it.
No, you disconnected.
Nice. The stream has ended.
Wait, how do I? Is it just 3 fingers? Right,
What?
okay.
Yeah, 3 fingers. The stream's ended.
He left. Oh, he's still here.
Holy fuck. No, it hasn't. Switch device. Your screen. Entire screen. Alright, go.
Okay. Wait, did you tell me to attendance?
I understand.
I
Just
will be
sit.
starting now. If you haven't already, please scan the attendance form, and we'll get started off with Maple. Then they'll be followed with a short catering break, and then MATLAB for the last hour. So you get started.
Alright.
Just be
Yeah. Okay, yeah. Alright, I'm gonna move on to the next slide if you guys have finished. Oh, is this too loud? Wait, is this too loud? Can you guys hear me at the back? Alright, okay. So, I'm gonna get started. Hopefully you've done the attendance form. Okay, so hello guys, my name's Orchid, this is Owen, and this is Maria, and we will be presenting the Maple part of today. And how this workshop is going to run is we will be splitting this into three parts. I'm going to be covering the basics, Maple functions, and basic calculus. Owen will be covering collections of expressions and complex numbers and equations, and Maria will be covering plotting and linear algebra. So if you have any questions that you see fall under those, just save them until we get to there. All right. Okay, basics. So I'm assuming a lot of you guys actually have prior experience with Maple, but you should know that Maple uses a lot of the basic operations. So for example, the plus sign for addition, the subtract sign for subtraction. And just keep in mind the asterisk is used for multiplication, the forward dash for division, and caret for powers. Okay. And just keep in mind that the two operators, if you have like a minus sign and another minus sign, if you put them together in Maple, that just does not compute because Maple doesn't understand what you're doing. So just always put a bracket or something to separate the two. So as you can see here in the brackets, if I wanted to compute something, for example, like -1 to the power of a half, if I just put -1 to the power of a half, that actually does not work because what Maple is understanding from this is that, oh wow, okay, she just wants -1 and then power it to the half. But what we actually want is, in this case, we actually want I, because what we're computing is square root of -1, which is I. Next, assigning variables. Most of you guys have already done this, so I'll quickly run over it. But in Maple, you tend to assign a lot of variables throughout using Maple. And what we use to assign is the colon equal sign. So for example, if I wanted to compute, let's say F1, and then we want to assign that the variable of 6, we just do that. And Maple just understands, okay, F1 is now 6. And it's also within Maple rules to just not use the equal sign when trying to assign a variable, because what they understand is, oh, if it's an equal sign, then it's just, oh, you're saying it's an equation. And Maple just doesn't assign it. And furthermore, there's another rule in Maple where, for example, if you wanted to assign a letter such as D as 1, 2, 3, or like something like that, Maple actually doesn't understand that either, because you would find out that D in later, we will go through this later, but D actually also means differentiate. So there's like certain values such as also pi where you just can't assign things because it already knows that pi is pi. So that doesn't work. And if we've assigned a variable and you're like, okay, well, I don't really actually want that variable to be F1 anymore or etc., you can just unassign it by just saying, oh, if we wanted to, we've previously assigned F1 as 6. If we wanted to unassign that, we'd say F1 equals, and then we use the quotation marks or the dash or something like that, and then we can, never mind, assign that as F1. Psych. F1. Okay, there we go. Sorry for the issues. But what that does is in the future, Maple will just understand that as f1, and it just unassigns it. And if you've previously already assigned a whole lot of variables and you just want to unassign all of them, you can just type restart. And Maple's like, okay, that's like deleting the history of whatever you've done for assigning variables. Next, I previously slightly touched on it, but there's certain constants in Maple that are already in the code. So for example, pi is known as just pi. I, the capital I, is used for square root of -1, and infinity is just representative of infinity. So for example, let's say, oh, and there's also another one where there's the percentage sign. When you compute something such as, let's assign A as pi. If we wanted to compute eval, let's say we want to know what 2 pi is, let's say, and then 2 asterisk, remember the asterisk, that would work. And for whatever reason you might need that value again, what you can do is just say the percentage sign. And that just uses your previous command. So it's a bit like, I don't know if you guys know, but on the handheld calculator, it's basically the answer button. So yes, there we go. Moving on. Like my previous example of the pi, you see here that there are actually 10 digits. That is the default version of Maple. They only go to 10 significant figures. But if there's a question that's asking for like 50 significant figures or something, you could edit this by saying digits and say 50. And by that, the next time you say, oh, I want to eval, let's say 2 pi again, that will give you 50 significant figures. And that for any other command that follows, so let's say we wanted to know what 3 pi is, it would continue on with the 50 digits. But let's say you wanted this to just be a one-time thing or something, and you wanted 20 digits for this specific question, you could just do eval 3, let's say 4 pi actually. And you do a comma and you say 20. And what that does is it only gives you the 20 significant figures for that specific one. But then the next one you do, it's going to be 50 again, because that's what we assigned previously. Okay, Maple functions. So Maple, as you know, there's expressions and then functions. So we previously just discussed that expressions, we can assign a value to a variable by using the := to define an expression. But once we have defined that, if you wanted to substitute a specific value into that expression, you could use the subs command. Where let's use this previous example here. So E equals x squared minus x. And if we wanted to substitute a specific value such as x equals 2 or something, we'd use the command subs x equals 2 into E. And then that would just give you the value. So that's quite an important one, substitute. And furthermore, there is also the one where you can differentiate a certain function. So you don't need to do it in your head or on the paper, which is just, if we wanted to differentiate E, we could do diff. You type the function first, and then you're differentiating it with respect to x. So you have to do a comma, and then press x. And that should give you the derivative of E. Okay. And there is also another one, because previously I used the subs command. If that is too much effort for some reason, you could also do this, which is, let's say we assign f this time. And instead of just writing the expression right after, we do an arrow symbol, which is just the minus sign followed by a greater than command, or greater than button. And then you could say, let's do the previous one again. And what this does is, if you want to substitute, let's say 3 into this, you can just straight away do the f followed by brackets with 3 in it, and that should give you the value immediately. So that's just also quite a simple way to immediately get substitutions in. Furthermore, we also are able to substitute values into functions that have more than one variable. So for example, we can substitute x, y, and z into the formula for the distance of a point on a 3D plane. So let's say, let's assign d as square root x, y, and z. And what I'm doing is making it easier for me to substitute next, which is instead of just having the x, like the previous example here, the x with an arrow, we're having x, y, and z, because in this function, there are 3 variables. So let's say square root of x squared So I've defined d as that function. And if you wanted to say, oh, we want to find the distance of point 1, 2, 3 from the origin, you could just immediately do 1, 2, 3. And that would give you the answer. And this is just for functions with more than one variable. There are also quite a lot of built-in functions for Maple. So for example, there is the absolute value function, which is just the 2 bars. But instead of putting in the actual bar on your keyboard, you do the abs, which is abs, and then let's say absolute function, absolute of x minus 2, and that would be the inbuilt command for Maple. There's also square root, sine, and if you wanted to do inverse of a trigonometric function, you would do arc sine, or arc cos, or arc cot. And those are the specific ones. And there's a lot more. There's also tan, etc. So some functions are stored in packages within Maple. So for example, if you wanted to do like linear algebra, or if you want to do plotting, which Maria will go into later, there is a certain package that you have to load first that then tells Maple, oh, I want to do plots now. So that is just with the with command. So you do with, and then you put in your parentheses, whatever package that you want to load. So I'll just do with plots. And what that does is it gives you a whole lot of things that Maple is now able to do. And after that, you can do like plot whatever function you'd like, and Maple would understand that. But if you didn't do that, Maple would just not understand what you're trying to do. Furthermore, there's also piecewise functions. So that's when, you have a specific function, and because of certain bounds, it's got different answers or different expressions that it's correlated with. So if we wanted to do a piecewise function for fx where it equals to 0, when x is smaller than 0, x squared when 0 is between 0 and 1, and when it's equal to 2x minus 1 for all x is greater than 1, we could do that as piecewise of, let's say, f. And then what you would do here to actually calculate the piecewise is you would type out the piecewise first. That's just how Maple understands it. And then you will type the condition first. So from this example, we had when x is smaller than 0, you would type x is smaller than 0, and then you'll type a comma, and then you'll put the value or the expression that you want. So for example, in this one, we said 0, so we're going to type a 0. And then what's going to follow next is, although in the one that is written here, it says, oh, it's from 0, where 0 is included, all the way up to 1. Maple, we don't need to specify to Maple that it goes all the way to 0, because we've already established in the first one, it is smaller than 0. So here you can immediately write when x is smaller than 1. And then you will follow that up with the certain condition that we're saying it is, so which is x squared. And here, for the last one, you can just immediately type without any restrictions 2x minus 1, because Maple will then understand, oh, this is just everything else that hasn't been specified previously. So you would do comma 2x minus 1. And then you do close brackets, and bam. That is what Maple will compute for piecewise functions. Furthermore, for when you're simplifying or, I don't know, expanding a certain function, there's several neat tricks that Maple can do that you don't need that you can just type in, so you don't need to work it out on paper or etc. So if you wanted to factor a specific function such as x squared plus 5x plus 6, although we could just inspect that, you could also type it out, factor, and then you would type out x squared plus 5x plus 6. And that would give you the answer for that. Furthermore, if you wanted to expand the function, for example, x plus 1 or cubed, So we could just say expand x plus 1 all cubed, and that would immediately give you the answer. So those are for the factoring and expanding. You can also try to simplify or normal to a certain like thing to produce a simpler form of your answer. So for example, if we wanted to simplify, let's say this complex thing over here, which is ln of 2x squared over 2 plus 2. Like, if the lab test was like, oh, this is the thing that you have to compute, and you wanted to simplify really quickly, you could just type that in, and I'm missing something. Oh no. Whoops, too many. There we go. And then it should just give you the answer really quickly. And furthermore, there is also one where you can normal. And the difference between simplify and normal is if we're working with like multiple fractions, for example. Oh no, what happened? If we're working with multiple fractions, the simplify would just immediately give you a denominator that isn't factorized, but the normal would give you it factorized. So let's say normal, we spelled that. Let's say if we're doing 1 over x minus 1, x minus 1 minus 1 over x plus 1. The normal would give you the answer with the denominator that is factorized. But if we use simplified here, simplify, it would just give you the answer when it's not factorized. So that's just the key difference between the two. And basic calculus. So in calculus, you will encounter a lot of limits, as you would know already. And Maple just helps you with that when you're trying to find a certain answer. So for example, if we wanted to find the limit of sine x over x when x is approaching 0, we would use the limit, ooh, wrong one, limit of sine x over x. And remember, you have to say what you're limiting it to, because if you just type that, Maple's just not going to know what you're actually trying to find the limit for. So remember to type a comma, and then you specify what we're trying to approach. So in this case, x equals 0. And that would give you the answer of 1. And furthermore, there's also, let's say, if we wanted to find the limit of 1 over x when x is approaching infinity, so we'll do x equals infinity, and that would give you the answer of 0. So that was just the limits, but if we wanted to find a one-sided limit, for example, in this case, we wanted to find 2 plus, we could also do the same exact thing, but let's say this example is limit of absolute value of x minus 2 over x minus 2. And if we wanted to find the limit of it when it approaches 2 plus, we would add a right at the end because that's the one-sided limit that we're looking for. And then that should give you a positive answer because 2 plus is greater than 2, and that's under the denominator. And the numerator is always positive. But if, for example, we wanted to find the left side of this, we would type it left, and that would give you the answer of -1. And that's just how Maple understands it. Next, we have derivatives. I briefly gave an example earlier, but this is just a more formalized way of me telling you guys. But there are multiple ways we could say derivative in Maple. So, for example, if we wanted to just find the derivative of the exponential function multiplied by sine x squared, so let's say y equals exponential function multiplied by sine x over 2. If we establish that and we wanted to differentiate that, we could write diff y, and that is the function we're trying to differentiate. And then we need to also specify with respect to what. So in this case, we're differentiating y with respect to x. So we'd add a comma and then an x, and that should give you the answer. Furthermore, there is also another way, which is by saying, oh, in this case, let's use the previous example here. let's say y colon. But if you remember from previously, I used this thing where we specified with an arrow pointing to a specific variable. So we also do the same thing here, so x, and then we follow it up by the function, which is exponential function multiplied by sine x squared. This part is basically the same, but what you can do now is by using d, which we specified as, which is also meaning differentiate, we could, oh whoops, never mind, not f, y. There we go, that's the correct one. We could find the first derivative of y really easily and quickly like this. And if we wanted to substitute a specific value into this, we would say dy, and then we follow it up with whatever value you want to substitute. So let's say we want to substitute 1. We would do this, and that should give you the answer. And if you wanted to substitute, let's say 3, we could put 3 here. So that's just the nifty way of differentiating a function and substituting a value into it. And so that was just first derivatives. If we wanted to do things with higher derivatives, so for example with like, you know, derivative of like twice, if we're diffing it twice, there's also a way where we can just add x followed by a comma the number of times you want to differentiate it to. So for example, if we wanted to diff, let's say sine 5x actually, sine 5x, and we wanted to diff it, let's say 6 times actually, we would type x 6 times, 1, 2, 3, 4, 5, 6, and that would give you the 6th derivative of sine 5x. But if you're not bothered to type the x's too much, which I'm not really bothered, so I would sometimes just do sine. We would do the same thing at the first part, but instead of typing the x multiple times, we would do x, then a $sign, and then the amount of times you want to follow with the x. So, and that would give you the same answer. But this one, you need to count, this one you don't, which is, I feel like, a lot better. There is also another way where we could say, let's assign f with the arrow to the previous function that I mentioned, sine 5x. If we wanted to diff this, let's say 3 times, we could also use the capital D, and in square brackets, we follow it up with the amount of times we want to diff it to, and then we do parentheses f, and that would also just give you the third one. And if we wanted to do it 6 times to fact check with the previous examples, 5, 6, it would also give the answer here. There is also implicit differentiation that is part of the syllabus. So for this one, it's very similar to what I explained earlier, but it's just implicit diff, the command implicit diff instead of just diff. So if we wanted to find the slope of a tangent of the unit circle x squared plus y squared equals 1, we could just say, let's assign d as the implicit diff of that. We'd say d is implicit diff of x squared plus y squared equals 1. But here, remember, we have to follow it up with what we want to differentiate it to. So we want to differentiate it from y and x. Oh, what did I do wrong? Diff implicit. Did I misspell that? Oh, okay, I know what I did. Wait, no, I don't. Implicit diff. Okay, well.
Where you defined x? Or did you define y?
Did I define? Oh, I did define y. Okay. Well, in this case, I'm going to quickly undefine y. Thanks, Owen. I've undefined y, and then in this case, there we go. Thanks, Owen King. But in this case, you would get that the implicit diff is minus x over y. Furthermore, if we wanted to substitute a certain value, if we want to find the derivative at a certain point in this case, we could use the subs command, which I have used previously. So subs, and let's say we wanted to find at point half and then square root 3 on 2. We would say subs that. And then we would say y equals square root of 3 over 2. And then we'd say we want to substitute that into d. And then we'd do comma and then d. And that should work there. There we go. Nice. Furthermore, we have maxima and minima. So if we wanted to find the global maximum or whatever from a function, we could use the maximize and the minimize command, where, for example, if we wanted to find the global minimum of sine x plus cos x when the x values range from minus pi to pi, we could say minimize, and then we're doing sine x plus cos x. And we want to do that from the bounds of minus pi. So what you do here is you do an x equals the first bound, the most left one, and then you follow it up with 2 periods or 2 full stops, and then you do the second bound. And that should give you the answer. And similarly, it also works the same way with maximize. But if you wanted to find just the maximum of a certain function without any bounds, you'd, for example, say maximize. What can we do? We can do x times the exponential, so xp and what that should do is just computes the maximum of that specific function. You can also integrate in Maple. I love this function. I love this feature because I can't do integration. But in this case, let's say if we wanted to integrate x squared multiplied by sine x, we could just do f x squared multiplied by sine x squared. So we've assigned that variable. We've assigned f as x squared multiplied by sine x. And then we can integrate using int, which is the command for integrate. We'd integrate what we would put what we want to integrate first, so in this case f, and then with respect to x. And that should give you the answer. There we go. Furthermore, if we wanted to, oh, what happened here? Okay. If we also wanted to integrate, let's say, sine x, but within bounds this time, we could do int sine x. And then if we wanted to integrate it from, let's say, 0 to pi, I would do the same thing as x equals 0, then you'd follow it up with 2 dots, and then pi. And that would equal to 2. Okay, next, Owen will be covering collections of expressions.
I'll take it. Wait, can everyone hear from the back? Okay. So now I'll be going over the collection of expressions. Right. So first we'll go through sequences, right? Sequences is very similar to sets and lists, but the difference between a sequence and, say, a list, because say a list, is that these. So if I have S1 here, right? Let's do S1, say, equal to 3, 3, 3, right? If I have S1 here, that is four distinct objects inside of for the sequence of S1. But a list is just one object by itself, right? That's the main difference, right? Another difference is I can really easily append onto a list, a sequence, but it's really hard to append onto a list. Right, so another way to make this list is we can say S1 can be equal to $3.4, which basically says the sequence 1 is defined as 3 4 times, right, which will give the same should give the same output, right? And then we can also use intermediate value to define a sequence. Let's give a different example. Say S2 equals to, like, for example, k plus 1, where k is from, say, 1 to 3, right? The 2 dot dot just means 2, right? Which will, yeah, this is basically saying it's 2 plus 2, then 3, then 4, right? But in this form. Okay. And then let's go to sets and lists. We can turn a sequence into a set by using the curly bracket, like.
Delete everything they had from the previous one.
It's like curly. We can use curly brackets like just when you define a set normally. So we can say the set 1 is equal to curly brackets of sequence 1, which will give you that. From set theory, we know that one set doesn't count the repeated values. So in this case, it will just delete all the rest of the repeated values and remain 3. Remain only 3 in the set. And then if we look at, for example, the second value, we can do it using square brackets. We'll find that we can't find one because all the other values are deleted. And then we can turn a sequence into a list using square brackets around the sequence. Right. So list 1, let it be defined as sequence 1. You can see that a list remains still has the same order and cares about repeated values, right? But this again, different to a sequence, is one singular object, right? And then we can also call on to a certain range of, for example, I want the 3rd to 7th. For 3rd to 7th values of this list, we can use L1 using square brackets, 3rd to 7th. But this will return nothing because there is only 4 objects in this list. So for example, if I only want the 2nd, 3rd, and 4th object, we can say L1 is from 2. Return the objects from 2 to 4 in the list, right? Which will return you 3, 3, 3. And then we can call upon or access a certain item inside of the sequence using the square bracket as well, right? For example, if I want to change the 4th term into, for example, 15, in this case, let's do L1 with the 4th digit, let it equal to 15, right? And then you can see it returns the list 3, 3, 3 with the 4th digit, which we wanted to change to 15, right? So this is lists, but sometimes we get a list, but we say we want to change it into a set, or once we get a set, we want to change it back into a list or not. We can use this operation using convert, or just if it's from if it's on a sequence, you can just use the square brackets and curly brackets for the other. Let's give an example. So we have a sequence, say 1, 2. Right? If I want to change it into a set, we will just use the curly brackets again to say set, let it equal to the curly brackets sequence, right? Which will turn into a set. Very easy, right? And then let's say we want a list. We can say it's defined. Defined as this, right? Which will return you the list of the sequence 1, 2, right? But what if I want to change from a set into a list? We can say, using this convert function, convert st, which is our set, into a list, right? Which will then turn the set st into a list. Say if we call upon set again, it will return a list, but it wouldn't change the actual thing, right? So even if we call upon it again, it will become set. Right, but what if I want to say change the list back into a sequence, or change the sets back into a sequence? We'll use the function op. Let's say change L back. It will change back into a sequence. Yeah. And then we can do a little bit more operations onto the list and sequence, such as we can sum it all up or product it all up, right? And we can make we can do that. Let's define a list L1 as 3, 7, and 18. Right? Say I want the sum of all of that. Right? You can just use the function add here, and then k, where k equals to L1. Right? This is saying we add from k for every element inside of L1. which gives you 28. And we can check this by saying 3 plus 7, which is 10, 10 plus 18, which is 28. Right. And then we have a different function which uses multiplication instead of addition, which is MUL as multiplication. We can say k, and then k equals 1 to 10. Again, the 2 dots equals to 2, means 2, which gives you 10 factorial, right? Because you multiply from 1 to 10. And then not only this, we can also sum to infinity, right? So the add function, so we can also use sum instead of the add function, right? So sum 1, 2, to the power of, say, k equals to 1 to infinity, which will return you 1, right? Because the infinite sum from of 1 or 2 to the k is infinity. And then we can also we can also use like different operations to operate onto lists, right? So for example, we can find the how long a list is, or like replace a certain value inside of it, replace a certain variable inside the list, or even like apply a function to every single variable inside the list. And we can sort the list as well. Let's give an example. We have L1 as 3, 7, 18 times y, right? So we have a pronumeral inside the list. And then the function to see how long it is NOPS, N-O-P-S. And then you can say use the percent sign to get the to get the output from the previous output, which will give you 3, right? Because we have the amount of objects inside the list is 3. We have 3, 7, and 18y. Right. And then we can substitute a certain pronumeral using subs. We can say y equals to say pi, and then L1. It's saying that sub y equals to pi inside of the list L1, which will return you the list again, 3, 7, 18 times pi instead of y. But you can also apply a function onto all of the objects inside of the list with the map function. We'll map cos of L1, right? Which puts cos into which applies cos onto every object in the function. You can also sort a list using the sort function, which is just sort of the list -1, 2, 4, 9. Right, which sorts the function from smallest to largest. And then onto complex numbers and equations. Note that capital I is used to represent the complex unit, right? And then you can use the normal operations on complex numbers. And then if you use a square root function, you'll need to use eval f if you want an actual value. Right. Let's give an example. Say z1 that equals to 23 plus I. Divided by negative I plus 45 as an example, right? If we just press it, sorry. Where's my mouse? Right. It'll give you the Cartesian equation, but in fraction form, right? But sometimes we'll want the decimal form instead, right? This complex number is basically the same as real numbers. You can use eval f to find the decimal. You can eval f of z of 1, which will give you the decimal point to 10 significant figures. Right. And then we can use real and imaginary to find the RE and IM to find the real and imaginary parts of a complex number. Note that when you use the IM function, like the actual IM function you would use in complex numbers, it will only spit out real values. All right, let's give an example. Say we have, let's use Z1 again, equals to 2 plus 3 times I, right? If I want the imaginary value of Z1, it will give out 3, right? Not 3 times I. And then we can use argument and argument as to find the argument or angle of the imaginary number. Note that when you use argument, it will spit out an arctan, but not an actual value. If you want an actual value, you'll use eval f again, right? Let's give an example. So let's say angle equals argument of Z1, which of course gives you an arctan. And then we'll use, to find the magnitude, we'll use the absolute function. Right. Magnitude equals the absolute of Z1, which will also give you a fraction. If you want the actual value, use val f. And then if you want to conjugate a complex number, you'll use the conjugate function. Right. Conjugate Z1, which will give you 2 minus 3i. Okay. Now on to equations. Right? So equations is like we have a left-hand side and a right-hand side. Right? That's what we'll define an equation as. So equation Z1 will equal to 2 times x plus y is to 5. Right? That will be our equation, right? But sometimes when you do like simultaneous equations, you have to add 2 equations, like subtract 2 equations together, right? Maple allows you to do that, right? So let's give an example. Say we want equation 1 to plus, for example, I have the value, I have the equation 32 equals to x, right? 32 equals to x, right? This basically adds the left-hand side to the left-hand side and the right-hand side to the right-hand side, right? So in this case, we can clearly see that from the left-hand side, we added 2x plus y to 23, and the right-hand side, we added 5 to x, right? So that's how you would use this function, right? You can also divide equations over. For example, we can say equation 2 would equal to equation 1 divided by, say, 32 equals to x, right? So in this case, we can see that the left-hand side is divided by the left-hand side of the bottom equation. The right-hand side is divided by the right-hand side of the bottom equation. Right. Further, we can also use the function RHS to return the right-hand side of the equation, or LHS for the left-hand side of the equation. Let's give an example, right-hand side of, say, equation 1, which will give you 5, right? You can see clearly, right-hand side of equation 1 is 5 here. Right? And then we can also solve simultaneous equations or just normal equations. We can solve using the solve function. Say solve, we have 3 times x plus 4 equals to 5 times x, right? Which will give you the answer to. You sum it back in, you'll see that that is true, right? We can also solve equations that have multiple variables, but we have to define which variable we're solving for. For example, we can solve for the quadratic general equation of the quadratic formula. We have a times 2 to the x plus b times x plus c plus c 0, right? But if we just do this, right, it will give you like linear equations because it doesn't know which variable you're solving for. If we want to solve for x, we'll say comma x, which will solve for x, which gives you the 2 quadratic equation, the quadratic formula. You can also put it into a list and then because some questions will ask you to answer in a list. You can just S equals to the list of, yeah. You can also use from before. If I want the second answer, you can use S of 2. All right. And then for exact solutions, we can also solve also solve a simultaneous equation by setting up the equation and then say which ones we're solving for. For example, we can say equation 1 can be defined as 2 times x plus y equals to 5. Equation 2 can be defined as x minus y equals to 4. And then the variables can be defined as the set x comma y. Right. And then we can solve the two equations using the solve function. Solve equation 1 comma equation 2. No, you're using the set for the two different equations, and then you solve for the set of the two variables that you want to solve for, which will give you x equals to 3 and y equals to 1, or y equals to -1. But this doesn't actually assign x to 1 and y to x to 3 and y to -1. And if you want to assign, you'll use the assign function, and then like that. And then if you call on x again, it will return 3. If you call on y again, it will return -1, right? And then further, sometimes you'll solve, like, say I have three variables but only one equation. You will know that you wouldn't get like an exact solution set. You'll always get like a linear equation from one to another, right? So we'll say, for example, if we solve the set 2 times x plus y plus z equals 5, and we solve for the set x, y, z, right? Oh, wait, I have to, y and x is already. Right, it will solve for the linear equations of x in terms of each other. Okay. Now sometimes you can't get an exact solution and you have to approximate. So in this case, we'll use fsolve to get an approximate answer. And sometimes when you solve for an answer, it might not be in like a range that you want. You can also set the range or like codomain of what you want, right? So say we want to solve this quadratic, x plus 2 equal to 0 in terms of x, right? In this case, because if you check the discriminant, it will be less than 0. That means it will not have any real solutions, right? But we want complex solutions in this case. We'll just say, after x, we'll say, oh, we want the complex solutions as well, which will give you the two complex solutions, right? And then say if I want to solve this cubic, 3x squared plus 2 times x equals to 0, x. If we solve it like this, it will give you 3 solutions. But the question might ask, oh, I want the solution from -1 to 3 halves, right? What we can do is we can set the solution to be like from -1 to 3 on 2, which will eliminate the last solution and give you the the sequence of only 0 and 1. Yeah. And that's it for me. I'll hand it over to Maria.
Okay, just checking that everyone can hear me from the back. Yeah? Okay. So these are like the last 2 parts of the presentation for Maple, so I'll try and like not to drag it out too long. Okay. So basically, first you have like plotting in Maple, and first you can just start off by plotting a single variable, right? And so basically for that, all you have to do is just use the plot function. And so all you have to do is just like write plot and then your expression. So whether that's like sine x or like x squared, like any expression, and then followed by like a comma and then your variable. So your variable is like what your expression is in terms of. So like for example, if you have like sine x, then your expression is in terms of x, right? So your variable is just x. And then you write your minimum and maximum values that you want it to be like evaluated between. And the dot dot just like evaluates it between anything, like between those two values. And then you can do like a similar thing for the next one, but the range is just like the limiting like the y values between like which ones it's evaluated in. So for example, if I might just start a new document. So for example, if you do like plot of, let's say we want to plot x squared, right? And then we want it between x equals -1, oopsies, and 3. Then there you go, you get your parabola as expected, and that's between x equals -1 and 3. So it's not too like hard. Or we can also try like the tan x example. So for example, we just go plot tan x, x is between 0 to 2 pi, and we also want y between -10 and 10. Oops. What did I do wrong? Oh, sorry. Dot dot. And then there you go. So you see that we've got our tan function between 0 and 2 pi, and our y is limited between -10 and 10. Another way, if you want to plot like 2 or like more graphs together on the same plot, then all you can do is just set graphs to be like, let's say we want to plot like x cubed plus x plus 1 and 13x minus 15. Then all we do is just like write them in together, as you can see there, and then you follow the same like plot function. So let's say we've got like graphs are dot equals x cubed plus x plus 1 and 13x minus 15. And let me just fix that part. And then now we want to plot those graphs between x equals -2 to 4. Then there you go, you just get them on the same number line plane. And so yeah, you can see like both graphs are there, and from there you can like look whether you want like intersection points, like number of them, and you can just evaluate it for the question that you need. And then you can also do parametric plots on Maple. So like parametric plots are just like your x and y in terms of t, and both like follows basically like the exact same thing as just plotting a single variable function, except you just write in both of your expressions and then just like what you want t to be in between. So for example, like let's just plot, let's say we're going to plot cos x equals cos t and y equals sine t. So we've got plots of, so we've got cos t and we've got sine t, and that's, and we want it like, for example, let's say we want t is between 0 to 2 pi. And so you just get like your circle, right? And so that's like an easy way of getting a graph without having to like find the whole equation first and then trying to draw it yourself. But then you have to also be careful with this kind of thing, because if you set t to be something else beforehand and then you try and plot it and define t again, then you're going to get an error. So let's just see an example of this. So let's say we set before t to be 16, and then now we try and plot the same thing that we had before. So I'll just copy and paste it just because we're short on time. As you can see, we get an error because we first defined t to be 16, and then we're telling it to be between 0 and 2 pi. And so now we also have like polar plots and implicit plots. So as Orchid said before, there's such a thing called like a plots package, and from there you can, I guess, graph most of the plots that you require. So like the first couple that we did with just the plotting, you don't need the plot package, as you could see, but like for the next ones we will need it. So let's just first take it in, so with plots. And that's just like another thing that Orchid didn't mention before, make sure that you have the colon after with plots, otherwise you're just going to list like the available like things that you can do with it. So with that, just make sure. And so first we can do like polar plots, and that's just, once again, it's very similar to just plotting, except now you're just putting polar plot at the front, and you're just defining your expression, and you're defining what you want theta to be in between. So let's just say we want to plot the polar plot of 1 minus cos theta. So all we can just do is write polar plot with 1 minus cos theta, and we can define theta to be between 0 to 2 pi. And so there you go, you get your polar plot for that. So if you need like a question with a polar plot and seeing like the symmetry and stuff, then that's quite useful. And then, oh, why did we go to the start again? Okay. There we go. And you can also do implicit plots. So if you've got like your expression in terms of both x and y, once again, it's quite similar for all the plotting, except you're just changing it from plot to polar plot to implicit plot, and then you just write your expression, and then you're just defining what you want x and y to be in between. So like, let's say we want to plot, I'll just make more space down here. So let's say we want to plot xy equals 1. So all we write is just implicit plot, and then x times y equals 1. And then we want like x to be in between -2 to 2, and y to be in between -2 to 2 as well. And so you just get your hyperbola there, so that's quite not too bad either. And obviously you can do it with much more complicated equations. And with the uploading the with plots package, you only need to, once you've done it once, you don't need to do it again. So like, you don't have to do it after every single like plot that you want to do. As long as you just upload it once, you should be okay. And then now plotting data points. So there's two ways of doing this. So first you can just like give your list of points that you want to plot, and it can plot it to you in two different ways. So the point where you see here the plot points will draw the points, but then it will connect a line between all of them together. So like, I don't know what that would be useful for, but I guess maybe we'll decide that would be useful. And then and then for plotting, if you want another way, if you wanted to just plot the points without like connecting the line together, then all you have to do is just add on style equals point. So we can see like an example of this. So I can't copy this. Okay. So so first all you have to do is define your points. So let's say we want our points to be like 3, 0.14, 15, 2, and 9, 2. So I've set those. And then, so the first version is just plotting them and then drawing a line between all of them. So plot points. And so there you see like my 3 points are there and they're all like connected. A fun little little line there. And then we've got the second version where you just see the points. So all you have to do, you start with the same thing. So you do plot points, and then you add on style equals point. And so there you see, you're just graphing your points rather than connecting all of them together. And another like handy little trick is that if you have like a complicated kind of equation and you need like a really big set of points, you can do a little thing called sequence, and then you write in your equation, and then you just define between what your variable is, and then we'll evaluate it to you, and it will give you all the points. Because we're like a bit of time pressure, you can try this at home, because we don't have time for this, yeah. But it will give you the list of points as it looks like this. And so now we'll move on to linear algebra. So first, to create vectors, so in Maple, to define vectors, you just use the two little kind of less than and more than little triangular symbols, and then you write in your vectors. And so you can write vectors in two different ways again, because Maple loves to be fancy. So if you want to write a column vector, then you just separate your numbers by commas. But if you want to write a row vector, then you separate it by the little long vertical line that you use in like an absolute value. So we can just like see an example. I might just make a new one so that nothing messes up. So let's just say we want to define our u vector as like as 1, 2, 3, 4. And so there you go, you see that you get a nice column vector. And if you want a row vector, let's make our row vector v. We can do 1, 2, 3, 4. And there you go, you get a row vector. So that's like your two different ways of writing vectors. And yeah, that's not too bad. And now you can also write matrices in Maple. And so that's either, once again, that's why we learned this part here to write the matrices, because once again, you can write it in either row or column form. So for example, the first one here, as we learnt, that'll give you the row vector form, and then this one will give you the column vector. So we can just see like an example of one of them, because these will give you the exact same vector. So let's say we've got 1, 4, 7, and we separate it, 2, 5, 8, and 3, 6, 9. And so there you go, you've got your nice little matrix. And so as you can see here, for this we wrote in column form. And so you've got your 1, 4, 7, which is going down the column, and then 2, 5, 8, which is going down the column, and 3, 6, 9, which is going down the column. And so yeah, this will give you the same version. But as you see here, for example, our first vector is 1, 2, 3, and you can see that going through the row as well. And that'll be the same case for the other rows. And so, as Orchid mentioned once again before, there's a linear algebra package. So every time you have to use like any kind of function within linear algebra, you have to upload the command. So basically, that'll just go as with linear algebra. Oopsies. And don't forget your semicolon. And so now you've got it all uploaded, and you don't have to upload it again. And so a fun little trick that you can do with this, you can extract rows and columns by like indexing the vector object. So for example, let's just make our matrix, where they make it 1, 2, whoops, 1, 2, 3, 4. So we've got our matrix here. And then for example, let's say I want row, and then of matrix 1, and I want the first number, well, the first row, sorry, and you just get 1, 3, right? And I can do the exact same thing with like row 2, and that'll give me row 2. And like another way of doing this, you can just write M1, and you'll get the same row. So I guess it's like a fun little shortcut. And so you can do the same with the columns as well. So for example, column, where is it? Column M1, and you get the first column, and you can do it the second one as well. And so there's like a better way of doing this as well. So I showed you the row way, and then there's also a column way. And so basically, that's just by writing M1 to 2 of 1. And so you see here you get the first column as well. And it will give you the first 2 numbers of the column. And so now there's like some special matrices. So you can write identity matrices with the linear algebra package. And so basically all you have to define within it is just the rows. So basically just define how many number of rows you want. You can also do diagonal matrices. So they'll like, you just have to list out what values you want within it, as you can see here, so diagonal matrix. And then for matrices of equal elements, so you have to define the number of rows, as you can see here, then the number of columns, and the value of them. And then you can also write a 0 matrix. And so you just have to define the number of rows and columns that you want. Since we're once again short on time, you can try this at home. And also with Maple, you can do like the elimination that we learned recently. And so basically there's 2 ways of doing this. I might have to just explain it rather than showing it, but obviously first you upload like the linear algebra package, and then you can define your matrices here, matrices. And then this symbol here, the M making the matrix of A and B, basically they'll let you make the augmented matrix, and that combines the A and B together. And so now we can do row operations, right? So if you want to swap between row 1 and 2, you first have to write row operation, and then obviously write what matrix you're referring to. And then in brackets you write 1 and 2. So basically your first number and the second number are just like the 2 rows that you want to swap. And you can also add like rows together, as we've learnt in the method. So first that requires a % symbol, and then here you mention which rows you want to refer to. So you've got 3 and 1, and then basically since we're adding -1/2 of row 1 to row 3, you first write the row that it's happening to, and then to the second row which we're doing the operation, and that's the same thing at the bottom. If you want to skip doing all that work, you can first define your matrix again, and then there's just a command called Gaussian elimination. So that'll just let you get to the final answer that you got here, but in a second rather than like a couple minutes. And then you've got reduced row echelon form, and so that just like reduces it down even further. And then you also have a linear solve command, and so that just lets you solve AX equals B. And so you just, all you have to do is just write out your 2 matrices, and then just do linear solve, and then refer to the 2 that you're talking about. Once again, I would show it, but we don't have too much time. And so anyways, that's it for the Maple part of the workshop. Thank you for coming to Maple. Oh, thank you. Thank you. If you haven't done the attendance form yet, please do so. And now we'll have like a small little break with pizza, so you're welcome to stay around. And then after that will be the MATLAB part of the session.
You do really good. I couldn't show you. That's one of the 3.
But I have meeting at 6. What do you have meeting? What do you do? I'm outreach. Oh, that's so cool. Throw the camera. Oh my god. Don't remind me. I'll see you guys.
This one. Do you want to see this one? Oh yeah, you guys can feel free to dig in. Oh yeah.